How can a vast range of problems be framed as searches? This module delves into turning problems into searches using AI. Discover how states, actions, and goals are key in AI problem solving. Explore how problems can be framed as searching for solutions. Learn about states, actions, and goals in search problems. Understand blind and informed search methods using heuristics. Discover how AI plays games by anticipating opponents' moves. Learn how to handle problems that grow too large for simple search methods. Frame problems as states, actions, and goals for machines to search. Compare blind and informed search methods and their applications. Learn how computers choose moves in two-player games. Understand AI's decision-making processes. Grasp the importance of search strategies in AI. Most problems are essentially searches for solutions. AI describes problems in standard ways for efficient exploration. Define starting points, moves, and success for effective searching. Computers can outperform humans in searching for solutions. The trick is in methodical problem description. States represent current situations like a puzzle layout. Actions are legal moves that change states, like turning left. Goals are tests to know when success is achieved. Start state, actions, and goal. Form a problem's pattern. Adding action costs helps find not just any solution, but the best one. State space includes every possible situation linked by actions. Imagine it as a web of states connected by actions. Searching involves navigating this web from start to goal. Even small problems can have vast state spaces. Clever methods are needed to avoid checking every possibility. A maze can be framed as a search problem. State is the cell you stand in. Goal is reaching the exit. Actions include moving up, down, left, or right. The solution is a sequence of moves from entrance to exit. This framing applies to various scenarios beyond mazes. Search trees grow as machines explore paths. The root represents the start. Branches are actions. Leaves are unexplored states. Revisiting states can waste time without proper tracking. Real systems use graph search to prevent loops. Blind search lacks clues about the goal's location. Breadth first explores wide, checking all nearby states first. Depth first explores deep, following one path fully before backtracking. Breadth first is thorough, but memory intensive. Depth first is memory efficient, but may wander aimlessly. Breadth first expands search outward in rings. It guarantees finding the shortest path in moves. Memory use is high as it tracks the current frontier. It's reliable, but may run out of space on large problems. Breadth first is thorough, but resource intensive. Depth first follows one path to its end before backtracking. It uses minimal memory by remembering only the current path. It risks going down long, fruitless paths. Depth first suits deep solutions and tight memory constraints. Safeguards are needed to prevent getting lost. Breadth first checks all rooms near the lobby first. Depth first follows one corridor to its end, then backtracks. Breadth first finds the nearest exit but tracks many rooms. Depth first may explore the whole building before finding an exit. The choice depends on solution depth and memory availability. Not all moves are equal. Path cost adds them up. Optimal search seeks the lowest cost path, not just any path. Uniform cost search expands the cheapest path so far. It is a cost-aware version of breadth-first search. Shortest in moves and cheapest in cost differ. Know your problem's needs. Informed search uses heuristics for direction. Heuristics are educated guesses about distance to the goal. They help reach solutions faster than blind search. A good heuristic is cheap, accurate, and problem-specific. Beware of misleading heuristics that slow the search. A good heuristic is cheap to calculate. It closely estimates true distance to the goal. It should never overestimate if optimality is needed. Tailor heuristics to the specific problem. Avoid vague or misleading clues that slow the search. Greedy search heads toward the closest looking goal. It is fast, but ignores distance already traveled. A times balances traveled distance with estimated distance left. A times finds the cheapest path with a non-overestimating heuristic. It is the backbone of most route planners. A times scores options by adding cost so far and estimated cost. It expands options with the lowest total score. This rule ensures honest exploration without flashy distractions. A times returns the best path with sensible heuristics. It explores less than blind search, making it efficient. Games involve opponents trying to beat you. Adversarial search plans for the opponent's best replies. The machine anticipates opponent moves for robust decisions. It assumes opponents make the worst choices for the machine. Planning against strong play leads to better strategies. Minimax assumes you maximize your outcome, opponent minimizes. It works backward from the game's end to score positions. The machine picks the highest score at its turns, lowest at opponents. This ensures the best outcome against perfect defense. Minimax scales to complex games like chess. Alpha-beta pruning skips branches that won't change decisions. It avoids examining branches the opponent will clearly avoid. This doubles how far ahead the program can look. It is a key trick for strong chess programs. Pruning saves time without altering move choices. AI problem solving is about clever searches in vast possibilities. From blind to informed searches, each method has its place. Games add an adversarial twist, requiring strategic planning.